winding we connect our load to. So in a transformer you would typically see its primary have a few hundred turns of wire. However, each transformer is individually tailored to meet that of the voltage in your country, as well as the load on the transformer, how much power it's going to put out, etc. So it does vary a lot. But essentially we're just talking about the very basic fundamentals today of how a transformer works. And as mentioned, this red wire and plug is going to represent my primary winding. Now you have to forgive the fact that my primary winding here doesn't have a few hundred turns of wire in it, but nevertheless this is how a primary winding is wired in a transformer. We have live and neutral wires from our wall outlet. These connect to either side of the winding or either end of the winding. And you might be forgiven for thinking, well, it doesn't matter how many turns of wire I've got over here, isn't this a dead short between live and neutral? And if we're talking about DC power, yes, this would be a dead short if we powered it up with direct current. However, because naturally a transformer runs from alternating current or AC power, this does not act as a dead short when it's powered up. Because what happens when the power comes in from our walllet and it goes around and around our primary winding, which is surrounded by an iron core, this creates an alternating magnetic field, and it does not dead short live and neutral together. So now if you imagine we've got power coming in, it's going around our primary, creating a magnetic field. We can then, if we look at our mock-up secondary, we can place the secondary within this magnetic field, and this induces power into the secondary. So now we have voltage and power between these two contact points here, and our transformer is outputting power as it's supposed to. So we've covered the basics of how a primary and secondary is wired, and if you look at our basic transformer here, you can see it's got 4 wires, and you'd come to expect that on a transformer you would always have an even number of wires because there's only 2 ends to 1 wire, correct? Well, not the case, because some transformers can have taps put in somewhere along the windings. So on this transformer we've got 3 wires on this side and 2 wires on this side. So how does that work? Well, one of the windings, and this can be either the primary or secondary, can have a tap put in somewhere along the winding. So this is, a tap is where the manufacturer at some point in the winding came along and electrically connected a wire. So now between this point and either of these points I'm going to get a different voltage when compared to these 2 points on the secondary winding. Now, why is this advantageous? Well, you could have a tapped primary winding that can be used internationally. So across the world, as we know, there is all sorts of voltage, different voltages for wall outlets. This can range from 100 volts AC to 240 volts AC typically. So you might want a transformer that can run anywhere in the world. You're going to have a primary winding that can run off different voltages. So it's going to have multiple hookup wires for the primary. Similarly, you can have a transformer that has a multi-tapped secondary so that you have different voltages, different voltage outputs from the one transformer. You can also have a transformer that has multiple secondaries. So in this transformer we have 4 individual secondary windings, and we still only have the one primary on this side. So this is handy because now instead of having 4 individual transformers each putting out 1 voltage, this one transformer can put out 4 different voltages on 4 different secondaries. So what deciding factor determines the output voltage of the secondary? Well, this has to do with the relationship between the primary and secondary and the amount of turns they have on each winding. So let's make up a hypothetical scenario. Let's say we have 220 volts coming into our primary winding here, and our hypothetical primary winding has 100 turns of wire on it. And let's say our secondary also has 100 turns of wire on it. Because we have a 1-to-1 ratio between our primary and secondary, our output voltage is going to be exactly the same, 220 volts. But let's say we want to lower the voltage. Let's say we want to halve it. So we've got 220 volts coming in. We still have 100 turns of wire on our primary, but our secondary now only has 50. That means our input voltage is halved because we have half the amount of turns compared to the primary, and now we have 110 volts across our secondary. What if we want to increase it? Well, similarly, we can just increase the number of turns on the secondary. So let's say we increase the turns to 200, so now it's double that of the primary. That also means it's going to double the voltage, so now we're going to get 440 volts output from our secondary winding. So let's have a look at this toroidal transformer I purchased for an up and coming project. So over here we have brown and blue wires. This represents live and neutral. This is our primary winding, and then we have 4 wires over here. Now this transformer has 2 secondary windings. If we have a look at the manufacturer's label here, we can see that each secondary over here is rated for 25 volts and outputs 10 amps of current each. So there is a couple of ways we can configure this transformer to either increase the voltage or the current. So I'm sure you are all familiar with what this is. This is a humble AA battery, and if I measure the voltage, if you have a look at the multimeter readout, we can see that this battery puts out just over 1.5 volts. And I'm sure a lot of you are aware what happens when you put batteries in series. If we connect positive to negative on the batteries and measure across both batteries now, the voltage is now 3.1. Now similarly, with a transformer with multiple secondaries, we can do the same. We can wire both secondaries in series. So let's pretend I electrically connect yellow and black together. Now between orange and red, I'm going to get the voltage of both secondaries combined. So now I'm going to get 50 volts between these 2 wires. It's worth mentioning, however, that the current still remains the same. So each secondary was rated at 10 amps of current. We are still limited by that. We're still 10 amps of current, but we're now at 50 volts. There is another way we could configure the secondaries though. We could put them in parallel. So parallel, rather than connecting, if we go back to our batteries, positive to negative, we're going to connect both positives together and both negatives together. So this will not increase the voltage, but it will increase the current. And you'd wire it something like this. We've got we've got orange and black, and yellow and red. And this would now be in a parallel configuration where we get 25 volts, but we now get it at 20 amps of current. So let's talk about how to identify primary and secondary windings. Now in an ideal world such as can be found on my transformer here, the manufacturer has clearly labelled the colour codes for what each wire does. But sometimes we don't live in an ideal world, and you end up getting a transformer out of a skip like I did, which has 6 wires that are all colour coded white. Great. Now, we can't just use a multimeter alone to work out what the primary and secondary is. For example, I'll demonstrate. I'll get out my multimeter and I'm going to set it to ohms, and we're going to measure the resistance of the primary winding. So this transformer has only 1 ohm of resistance on its primary winding, and if we connect up our multimeter to the primary winding on this little transformer, there we go, we can see it's got a resistance of 231 ohms. So both of these transformers are designed to run off 220 volts or thereabouts, and both have vastly different resistances on their primaries, so we can't use a multimeter alone to work out what a primary and secondary is. So to correctly identify a primary and secondary winding on a transformer if they aren't clearly labelled obviously takes a bit more than your garden variety multimeter can offer, and I'm not going to go into detail of how this is done and what equipment is needed unless you guys want to see that in a future video. However, if you are salvaging a transformer from an appliance such as this microwave oven transformer, the easiest thing to do is to simply trace the power cord all the way to the transformer. The wires from the power cord, these might pass typically through a fuse or a switch, but will eventually lead to the transformer found in the appliance, and this will typically be your primary winding. So that's the easiest way to identify primary winding on a salvage transformer. So as I mentioned earlier, I purchased this transformer for an up-and-coming project. However, the AC output from the transformer is no good to me. I can't use it. It needs to be rectified to DC power. And to do that, it only takes a couple simple components: a capacitor and a full bridge rectifier. And this is what I'm going to discuss in my next video. I'm going to discuss how to choose the correct capacitor and also the correct full bridge rectifier. And if you want to see that, click the link up in the video's corner here. So hopefully you found this video informative, and it gives you a little bit more info on how a transformer works and also how you can use it in any projects that you may need. So if you found this video useful, please give it a like, it'll be much appreciated, and if you have any questions, leave them in the comment section down below. Other than that, thank you very much for watching. I'll see you in the next episode. Bye for now. So in this video, I'm going to be talking about how you can choose the correct size capacitor and full bridge rectifier to convert AC into DC power. I was discussing transformers. So in this video, we're going to discuss all about transformers and give a basic insight into how. So in this video, I'm going to be talking about how you can choose the correct size capacitor and full bridge rectifier to convert AC into DC power. So in a previous video I was discussing transformers, and also I stated the fact I needed to rectify the AC power from my transformer here to DC for an up and coming project. And that's what we're going to discuss in this video. I'm going to discuss how you can choose the correct capacitor and also full bridge rectifier, and I'm going to go into a little bit of basic detail what these components do and how you can choose the correct voltage and capacitance, etc. for your specific application. So let's get into the video. So the first component I'm going to talk about is the full bridge rectifier. So what is a full bridge rectifier? Well, in a nutshell, its job is to convert AC to DC power. If we look at the top of this example, you can see we've got in two corners hyphen squiggle marks. This is for the AC power input. Doesn't matter which side goes to live or neutral, or the output from your transformer. And then on the other two corners we've got a plus and minus symbol, and this is for our now rectified DC power output. So our input power would go on these two junctions here, and then we'd get DC power between these 2 points here. But looking at this package, it's a bit confusing to see what's going on. What's inside a full bridge rectifier like that is actually a set of diodes in this configuration. So a full bridge rectifier is nothing more than 4 diodes configured to rectify AC power into DC. So much like the package over here, that's a full bridge rectifier, we have 2 inputs for AC, and then we get positive and negative on these 2 outputs here. And in a nutshell, a diode, if you don't know what it does, is a semiconductor which allows electricity to flow in one direction and then blocks it coming back from the other. So now let's move on to how to choose the correct diode or full bridge rectifier for your application. So this is the full bridge rectifier I chose to rectify the power output from my transformer I showed earlier for my up and coming project. And now I want to discuss how I went about choosing this full bridge rectifier. We need to look at how much voltage it can handle, how much current it can handle, as well as how much heat is going to be generated when max current is passing through this full bridge rectifier. So we need to find the data sheet for whatever full bridge rectifier or indeed diode you choose to use. So now let's go have a look at the data sheet for this full bridge rectifier. So here I have the data sheet for my full bridge rectifier. If we scroll down, we're going to take a look at the maximum reverse voltage, maximum average forward current, and forward voltage drop. And this is all the symbols for them: VRRM, IF, and also VF. So let's start off by looking at the voltage. So once the power has been rectified, my full bridge rectifier is going to output 70 volts DC or thereabout, and I typically like to add around 20 to 30% headroom. So I am looking for a full bridge rectifier that is around about 100 volts or more, and the model I bought is a -01. So I bought a full bridge rectifier that's rated for 100 volts, so we're all good there. The next thing to look at is how much current we're going to need to draw from our full bridge rectifier. Now my transformer can output 10 amps continuous, and again I typically like to add about 20 to 30% headroom minimum. So the model I bought is a GBPC15, so therefore it's rated for 15 amps continuous. So again, we're all good there. The next thing we need to look at is the forward voltage drop, or VF. Now this is rated at 1.1 volts. Now what is a forward voltage drop? Well, any diode typically has a voltage drop across it. So what that means is if we put power through it, we're going to get slightly less power out of it. We're going to get a voltage drop, and in this case it's 1.1 volts. Now why is this important to consider? Well, 2 things. If you expected to put in 5 volts to your full bridge rectifier and you're going to get 5 volts out, that's sadly not the case. If you put 5 volts in, you're going to get 3.9 volts out. You're going to see that 1.1 volt drop, irrespective of the input voltage. Also, we need to look at how much heat we're going to need to dissipate from the full bridge rectifier. We might have to consider adding a heat sink. So we all know that voltage times current equals watts. So what I'm going to do is calculate how many watts of heat is going to be generated if I pass the full 15 amps of current through my full bridge rectifier. So to calculate that, I'm going to first enter in my VF, or forward voltage drop, which in this case for my full bridge rectifier is 1.1 volts, and I'm going to times that by the maximum current of the full bridge rectifier, in this case 15 amps. I'm going to hit equals, and therefore we're going to get 16.5 watts of heat generated from our full bridge rectifier at maximum current. And this isn't to be ignored. That is going to be quite a significant amount of heat if it's sustained for a long time at 15 amps, so we should consider adding a heatsink to our full bridge rectifier. We can also see that the manufacturer had in mind that this full bridge rectifier is going to generate a bit of heat by the fact that we've got a metal surface here, and what we can do is get a heat sink and we can bolt this full bridge rectifier to it with a bit of thermal compound to help dissipate the heat generated when we're pulling the full load through this full bridge rectifier. So now let's move on to capacitors. So the type of capacitors we're going to be shopping for to smooth out the power from our full bridge rectifier are called electrolytic capacitors. Now, this capacitor has two ratings listed here, 50 volts and 4,700 microfarads. So let's discuss these figures. So 50 volts is the peak voltage this capacitor is rated to handle. Any more than that and you risk damaging or even exploding the capacitor, which can be quite fun. But not if you want a reliable power supply, then it's bad. So again, we're going to be looking for a capacitor that is around about 20 to 30% rated higher voltage than the voltage we're going to be running. So in my case, it makes sense to buy a capacitor that's rated for 100 volts or higher. Next up, we're going to be looking at capacity. So 4,700 microfarads is the capacitance of this capacitor I've got here. But how do we choose what size capacitor we need? Well, this is based on the frequency of the AC power rectifying, the amount of current we're going to be drawing, as well as the acceptable voltage drop. So when power is rectified into DC after our full bridge rectifier, it's not actually smooth. There's momentary lapses where there's no power, and what that means is we've got power, no power, power, no power, and we're going to not get a smooth voltage. It's going to have ripples in it. The capacitor's job is to smooth out those ripples so that we get much more stable power. So let's discuss how to choose the right size capacitor. So here is the formula for calculating our capacitance. Current times half cycle time divided by acceptable voltage drop equals microfarads. So let's break this down. First off, we need to establish whether our wall outlet outputs AC power at 50 or 60 Hertz. Now here in New Zealand it is 50 Hertz AC, so my half cycle time is 10 milliseconds. Next off, we need to work out what our acceptable voltage drop is going to be. So for my application, the peak voltage I'm going to get after rectification is 70.5 volts DC, and the minimum acceptable voltage I can have is 65, so this gives me a difference of 5.5 volts DC. So let's break this down. Let's use this as an example. In this example, I'm drawing 10 amps of current maximum, so I'll put in 10 amps in my calculator. I'm going to times that by my half cycle time, so in this example I'm going to use 8.3, so times it by 8.3, hit equals, and then my acceptable voltage drop is 5.5, so I'm going to divide 83 by 5.5, and then we get a microfarad capacity of 15,090 microfarads. So chances are the capacitance you require is not going to be found on an off-the-shelf capacitor. You might turn up an obscure number like 1,111 microfarads, and you're not going to find that on a capacitor. So what do? Well, we buy a capacitor that's rated higher than we need, but is closest to what we need to save on money. When it comes to wiring your electrolytic capacitors, make sure you wire them the correct way, because most electrolytic capacitors are polarity sensitive, and if you get it backwards, then chances are you're going to have a nasty explosion on your hands, which does add a bit of drama in your life, but does make for a rather poor power supply. So other than that, thank you very much for watching. If you have any other questions, drop them down in the comment section below, and also be much appreciated if you can give the video a like. Other than that, thank you very much for watching. I'll see you in the next video. Bye for now.